For the last talk of the session, we have higher order model checking of effect handling programs with answer type modification, and Taro Sekiyama will be giving the talk.
All right, thanks for the introduction. So I'm Taro Sekiyama, and this is a joint work with Hiroshi Unno. I think he would be in the venue. And this talk is about high order model checking for programs with algebraic effect handlers. So the model checking is one of the most successful verification methodologies, and it takes two inputs. The first input is systems, which may be programs, graphs, or state transition systems. And the second input is properties, which can be expressed as temporal logical formulas or automata, usually. The model checking problem is to decide whether the system M satisfies the desired properties phi. The higher order model checking is an extension over model checking to higher order programs. So here the systems is represented by the higher order program that yield possibly infinite trees. So systems may be higher order recursion schemes or PCF terms. And the properties is predicate over infinite trees, and which can be expressed as some logical formulas or tree automata. And the higher order model checking problem is to decide that trees generated by the system M satisfy the desired properties. And it can encode many kinds of verification programs, including safety and liveness verification programs, such as assertion checking and termination or non-termination analysis. One of the advantages of the higher order model checking is that it is decidable if the data domains are restricted to be finite. But to apply the higher order model checking to real-world software systems, it would be desired to support the effectful programs. Actually, so far, there are several studies to support the effect, such as non-deterministic choice, exception handling, and resource handling, such as files. But there are more effects not supported yet. For example, mutable store, IO effect, backtracking, coroutine, and so on. So it is desired to develop a general framework that can support these more effects. At this year's proposal, the Dal Lago and Ghyselen presented extensions of higher order model checking to algebraic effect and effect handlers. And algebraic effect are mathematical abstractions, and they can express many kinds of effect, like the global store, IO effect, and non-deterministic choice. And effect handlers can provide the ability to access the delimited continuations with the user. And the abilities makes it possible to express a continuation-based effect, like the exception handling, local store, and backtracking, and coroutine, and so on. But the problem is that the higher order model checkings for effect handlers is undecidable. This is because effect handlers can encode natural numbers, and the higher order model checking programs with infinite data domains, like the natural numbers, is undecidable. But this is not the end of the story. A natural question is that what fragment where higher order model checking is decidable? And we tackle these questions. And in this work, we identified a rich class of higher order programs with effect handlers, where higher order model checking is decidable, and effect handlers are still expressive enough to implement many kinds of effect. Our key idea for that restriction is to restrict the use over delimited continuations, and we use answer types and answer type modification to implement the restriction. And we also defined CPS transformations, which can remove effect handlers, and we use the CPS transformation to prove the soundness of the higher order model checking for the identified fragment. And we also use CPS transformation to implement our model checker for higher order programs with effect handlers. But I will skip the implementation part in this talk. Okay, this is a summary of our work. So from now, I will explain the more details about our work. But before that, I want to explain more about the background. So the higher order model checking for effect handlers are studied by the Dal Lago and Ghyselen, and they target the language called HEPCF. This language supports higher order functions, fixed point combinators, and finite data domains like Booleans, and effect operations and handlers. And in this language, effect operations is described like this one. Here, this is a call of operation OP, which takes the argument value P. And M represents continuations of this operation call. And X represents the result of the operation call. And M can reference the result using the variable X. And if the operation is called in some context, then the operation bubbles up using the first reduction rule. It means that if the continuations of the operation call is M2, it is pushed into the continuation part of the operations, like this one. And the operation is handled by the effect handlers, and to make the handlers active, we can use the with handle construct, this one. And here, I suppose the operation OP is called, and H provides some implementations of the called operations, which is named M prime here. And then the operation implementations of operation OP provided by the H is executed. But here, M prime may contain the free variables X and K, which represents argument and continuations of the operations. So these variables are replaced by the corresponding values. Okay, and so then actually using a variable K, M prime can access to the delimited continuations. Okay, but this is a reduction semantics, but to formulate a higher order model checking, the previous work also defines tree semantics. In the tree semantics, programs generate trees called effect trees. So let's see one examples. So this is in this term, the three operations are called ask, tell, and raise. So here, from this program, we can generate effect trees like this one. Here, nodes are labeled with operations used in the original program. So because in the original program, the operation first invoked operation is that ask. So then the root node of the effect trees is labeled with ask. And in the tree semantics, handlers carry out folding of effect trees. And the handled effect do not appear in the generated effect trees, and only unhandled operations may appear in the trees. So in these examples, the operations tell is handled by some effect handler. So then in the generated effect trees, tell does not appear. But the other operations, ask and raise, can appear because it is not handled in the original programs. Okay, and using this tree semantics, we can formulate the higher order model checking for effect handlers. In the model checkings, first we generate the effect trees from the given programs. Then we can check that the generated tree satisfies given desired properties. But for example, the property can state that no raise operation is called in the program. But as I said, this model checking problem is undecidable, at least if the phi is expressed as MSO formulas. because effect handlers can encode natural numbers. Okay, and to see the problems, let me re-examine the encoding of a natural number proposed by the previous work. And the point is that natural number n is encoded using the other n calls to some specific operation sub here. And the case split on the natural numbers can be encoded using the effect handlers. Okay, and using this encoding, for example, we can implement basic arithmetic operations, especially the subtraction v minus n can be implemented using n effect handlers. Okay, this is a problematic encoding, and we want to reject the program in using this kind of encoding. So our key idea to prevent the natural number encoding is to bound the number over simultaneously active effect handlers. So okay, so let's see what it means. So more formally, this restriction can be stated like this one. So here, E is a term to be model checked. Then there exists some natural number n that bounds a number over effect handler that appears at runtime and simultaneously handles the effect of some term E prime here. And active effect handlers means that effect handlers in the state of obeying the effect of some term. Okay, so then why does this restriction prevent the encoding? So to see it, first, please remember that the predecessor of natural numbers is implemented by effect handlers like this one. And by bounding the number of simultaneously active effect handlers, we can bound the number of applications of the predecessor. So then, as a result, we can bound the range of the accessible natural numbers by imposing the restriction. It means that under the restrictions, we cannot access the unarbitrary natural number. So then it means that the natural numbers cannot be encoded completely. Okay, so this is the basic ideas of our restrictions, and the next question is that how we can enforce such restrictions. Our approach to implementing the restriction is to introduce a type system with answer types. And answer types are types over delimited continuations. And the distinguished point for our work is that answer types can reveal the number of delimited continuation necessary to evaluate terms. And the number of delimited continuations correspond to the number of effect handler that can be active at the same time. So by bounding the size over answer types, we can bound the number of simultaneously active effect handlers. So this is ideas why the answer types can work to implement the restriction. Okay, and this is a type language in our type system. The most important gradient is that computation types here, and the sigma is operation signature, but it's not important. So let me omit it. And T is a value types, which represent what values are produced by the terms of these computation types. And the remaining two types is answer types, and which are either over value type or computation type. And the first answer types is called initial answer type, which represents the return type of the delimited continuation enclosing the terms of this computation type. And the second answer type is called final answer types, which represent what the meta context expects for terms. And meta context is a context that enclosing the delimited continuations. Okay, so maybe for someone familiar with the CPS transformations, one way to understand this type of language is to check the CPS interpretations. So this is our CPS interpretations for the computation types. Here we can find that the T1, value type T1 and initial answer type A1 can make the type over continuations. And then the meta context can provide the continuation of this type, and then you can get the result of the type A2, final answer type. Okay, and in our type language, computation types can take this form in general. Here, which consists of the n pairs of value types and initial answer types, and then it ends with some value type. Then the CPS interpretations of these computation types can be given like this one, and it means that the computation types can take only the n continuations. So then it means that the number of continuation passed to the terms is bounded statically. So this is why the answer types may work, can work for the implementing the restriction. Okay, and the result is that we can show that the model checking for higher order programs with effect handlers is decidable if the program is well typed in our type system. We prove it using the CPS transformations, but I will skip the details in this talk. So please check out our paper if you are interested in the detail. And we also confirmed that our type system can accept many effect handlers, like the exception handling, local store, backtracking, and so on. This is because our type system restricts the use of effect handlers, but not the effect handlers themselves. So then our type system can accommodate many kinds of effect handlers. Okay, let me conclude. So we show that the higher order model checking for effect handlers can be made decidable using answer types. And our work is one example that shows that answer types are an effective tool in reasoning about effect handling programs. Yeah, that's it. Thanks for listening.
Great. Do we have some questions? Yes.
Did you do any examples of things that are checkable? Like, did you get some benchmarks on it? I'm just curious if it actually worked in practice, given the restrictions you put on it.
Yeah, and we use the examples with local store and exception raising operations, but it is still a small examples and small specifications. So the experimental result is promising, but we don't test it in the bigger examples.
Any other
questions? Can you think of your can you think of your approach as having some relationship to bounded model checking?
Oh.
It seems like you're using answer types to put a bound on the search space that maybe is similar to what bounded model checkers do.
Yeah. Right. Okay. That sounds interesting question. So I have no concrete answers, but it might be possible to formulate our idea as a bounded model checking extended for the higher order model checking, higher order programs. Yeah, that may be an interesting question, but I'm not sure the answer.
Sure. Okay. So another question, I guess maybe this follows up on the earlier one, but is there any prior experience with I'm not familiar with answer types myself. Is there prior experience with kind of how restrictive these are on programs? I'm wondering, what are there kinds of program uses that are likely to be prohibited by this, and are there conversely classes that are likely to be fine?
All right. So yes. So maybe one of the problem is that it's related to the restriction proposed in the this type system. So one thing is that answer types can bound the number of effect handlers. So it means that we need to constrain the number of effect handlers used at runtime. So I'm not sure it is okay. So it may be problematic in considering the modular verification because we need to know the what number of effect handlers are used before model checking, right? So then it might be difficult to verify the programs in modular way in the presence of the answer type modifications. It's one of the critical problems, I think.
Okay, yeah. So I imagine something like exceptions. You're typically not throwing lots of exceptions in a program, so I would expect that to be bounded. But I wonder, like another use of effects is for something like coroutines, like yielding.
Right.
Yielding things, and maybe if you don't have a bounded data structure, would that be an example of something that would be hard to type with answer types?
Right. I think actually we are considering the application in such a context. So maybe a concurrency or user level thread scheduling. Yeah, I think it's a promising direction for future work.
Yeah. Okay. Good. Any final questions? If not, then let's thank the speaker again.